Hi there. Today we'll look at Underspecification presents challenges for credibility in modern machine learning by Alexander Damour, Catherine Heller, Dan Moldovan, and literally all of Google. All of Google is on this paper, including some others, including MIT and Google with a white space, but there is a lot of authors here. And not sure what they all contributed, but the main authors are three main authors, which I guess is legit. But this more looks like some kind of a physics paper from CERN. But we'll dive into what the paper claims. It's sort of a paper that looks at a higher level onto machine learning pipelines, but gives very concrete examples for what it's talking about. So the problem that the paper identifies is this thing they call underspecification, which is sort of related to problems we had in the past or that were identified in the past, but they make a clear distinction of what underspecification is to what problems it leads and how that manifests, and also what the causes are to an extent. Well, it's a very long paper. I think it's some 30 pages long, the main text or so. So we won't go through all of it. I'll pick out some parts of where I think are relevant to the main story. I'll criticize it a bit because I think it warrants a bit of criticism. And yeah, that's what we'll do. So bear with me. If you like what videos like this, don't hesitate to share them out and tell your friends about it. Also, let me know what you think in the comments. I think this is a good topic for discussing things. The question to keep in mind while going through this paper is, do they really demonstrate what they claim? So that was my kind of question when going through some of this. So let's actually just dive into the abstract. They say ML models often exhibit unexpectedly poor behavior when they are deployed in real-world domains. I think we all get a sense of what that means, and we all know of examples when ML models perform fine in our lab, in our training data and test data, actually. But then when we deploy them into the world, they're not doing so fine. I say we identify underspecification as a key reason for these failures. They're not saying it's the key reason, it's a key reason. So that's the important thing. Now they define it. They say an ML pipeline is underspecified when it can return many predictors with equivalently strong held out performance in the training domain. Underspecification is common in modern ML pipelines, such as those based on deep learning. So I think the sentence isn't really complete here. So it's underspecified when it can return many predictors with equivalently strong held out performance. So what that means is you have some sort of a test set, right? Big data set. Train. You have a big training data set. You train your model on that, and then you test it on a test set. And the training and the test set, they usually come from some sort of distribution, and what often happens is you simply split your data into a train and a test set. And with that, you measure some sort of generalization capability, right? So there are a number of assumptions here, namely that this is sort of an IID distributed data cloud. And the assumption is basically that the test data, the data to which your model will be applied in the real world, is sort of similar to data you've trained it on. And if that is the case, then a procedure like this will give you a fairly good estimate of how your model is going to perform in practice. However, you then take that model and you deploy it to the real world. And the real world, I'm horrible at drawing real worlds, but in the real world, you might have, this is Europe, yay, Africa. In the real world, you might have very different distributions of data, and the model might not perform as well anymore. So this, of course, they're not the first ones to notice this particular problem, the fact that there's distribution shift and so on. What they are saying is that this procedure up here, let's say it's a deep learning system. There are many local minima of that deep learning system. So that starts from your choice of optimizer, your choice of batch size, hyperparameters, the choice of architecture of your network, and so on. So there are a number of hyperparameters, let's call them all hyperparameters, even like the different procedures and so on. So there are a number of hyperparameters: learning rate, architecture, the batch size, all kinds of stuff. What they experiment here with is the most innocuous of hyperparameters, which is the random seed. So even if everything else stays the same and you switch up the random seed, you necessarily go into a different local minimum, right? All of these give you different models. We know that in deep learning you have sort of a lot of local minima, actually. Like you have a continuum of local minima. They are all as good as each other, and notably, so these are training models, notably they all perform quite well on that test data set, right? So you train any of these models, maybe you switch up the random seed, and most of them will actually work quite well on the IID test data set. However, they will exhibit very, very different performance when you apply them to the real world. So maybe this model here, you apply it to the real world and it works equally, it also works well, but maybe this model right here, you apply it to the real world, it all of a sudden doesn't work. So the underspecification problem that they identify is when all the models work well, all the models from your training procedure work equally well on the test set. However, they perform very differently in the real world. Namely, there would actually be at least one model, like this one here, that does perform well even in the real world. However, there is another one, at least one other, that doesn't perform well like this. So the pipeline is underspecified. This train-test split simply doesn't capture the variation, that some important property of the real world. So the pipeline that produces the model doesn't care about that feature. So it's pretty much random whether or not that feature will be included or excluded or important or not important. And it's pretty much depends on which local minima you happen to be in. And just by looking at the test set, you can't differentiate whether or not that model will perform well in the real world or not. This is underspecification. It's very different from the usual domain shift argument. Usually you say, well, the test set simply isn't the same as the real world, and therefore the model performs well on the test set, but then in the real world, not so much, right? Here, it's more specific. You say there would be one of these good models that we get out of this procedure, one of the random seeds would actually work well in the real world. However, another one doesn't. So of course that is a problem, and they so the way they go about the paper is they say they give some examples of how that is, and in my opinion the examples don't really convince me. Like, I see their point, however the examples are, let's say, half convincing. And then at the end they give some recommendations for, I mean, there is some work in this, namely what you have to do is you have to add constraints, right? If you want to solve this problem, there's two ways. Either you can test models, you can take all of the models that come out of your pipeline, test each one of them on the real world, on the things you care about, and the one that works, you deploy that. However, it means that you then again need some kind of test data set from that real world. The other way is to actually, since the model is underspecified, try to bring in more specifications that you care about during the training pipeline, making sure that this model that you care about is the one that actually turns out to be returned. They don't demonstrate this here. So this is my criticism. They demonstrate the problem. I think they demonstrate the problem in a way that doesn't convince me. They also do not demonstrate a solution. So they don't ever go ahead and say, now we actually perform this additional specification and look, what turns out is still a good performing model, but with that thing fixed. They don't do that. Yeah, so that's, keep an eye out for that. So we'll go, as I said, through the paper. But first, a bit more of the abstract, so you just hear it in their words. They say predictors returned by underspecified pipelines are often treated as equivalent based on their training domain performance. But we show that that such predictors can behave very differently in deployment domains. This ambiguity can lead to instability and poor model behavior in practice, and is a distinct failure mode from previously identified issues arising from structural mismatch between training and deployment domains. So that's what I said. It's a different problem than the classic domain shift or data drift or whatever you might want to call it. We show that this problem appears in a wide variety of practical ML pipelines using examples from computer vision, medical imaging, yada, yada, yada. Our results show that the need to explicitly account for underspecification in modeling pipelines that are intended for real-world deployment in any domain. I mean, yeah, fair enough. This is actually a problem, right? And if you deploy ML in the real world, you would be, it's very appropriate to actually care about these types of problems. I'm not saying you shouldn't care about this. So let's go to actually jump in the first example. So they have this notion of what they call a stress test. Okay, so a stress test is, as I understand it, is nothing else than you test whether or not you test like one particular aspect of the model. So they're going to have a couple of examples. One example, they have an NLP pipeline where you're supposed to, infer, do pronoun resolution. And the stress test, one of the stress tests would be whether or not that model is sensitive to gender stereotypes. Okay, so the assumption is kind of pronoun resolution should be like just linguistic thing. It shouldn't really have any bias towards any gender stereotypes and whatnot, or maybe not overly so if you compare it to actual world biases. And the stress test would be, let's measure that particular dimension, so this gender stereotype dimension in the model, and see how that performs. So that's the stress test. And what we are specifically looking for is there a large variance? So is there models that behave the same on the training and the test set, but have a large variance in these stress tests? So the first model here is this epidemiological model. So they say a simple epidemiological model, which appropriate for our times, I guess, specifies how infectious disease moves through a population given certain parameters, right? So there are two parameters. You can see the differential equations right here. There are two parameters, namely there is this beta right here, represents the transmission rate of the disease from the infected to susceptible populations, and the parameter d, which is this thing here, represents the average duration that an infected individual remains infectious. So once you plug in those parameters and you start with like some initial population, I guess the susceptible population. This S is susceptible, I is infected, and R is recovered. So you start with 100% susceptible, and then you let this, and 0 infected, 0 recovered, you let this play out and you see how well that works. So this is a model, and it will give you curves like this, okay? So you can see depending on the D parameter and the beta parameter, you have different curves like this. They all sort of look like this. So here is number of infected. At the beginning, it's 0. And then, of course, it shoots up. But then as kind of herd immunity, I guess, kicks in, this goes down again. So it's quite a simple model. And what their goal is here, they say, look, let's say, just hypothetically, this is the beginning of a pandemic, just making this up. And I give you some data points, right? So at the beginning, we're at 0. Then we have some, then some more, then some more. Now, please predict the trajectory of this epidemic from these data points. So what you want to do is you want to fit these two parameters to the data points. There is actually a unique solution. However, because of the exponential rise of the trajectory, the solution is numerically not well specified. Okay, so they say, importantly, during the early stages of an epidemic, when the observations are small, the parameters of the model are underspecified by this training task. This is because at this stage, the number of susceptible is approximately constant at the total population size. At the total population size. So that means if you have low number of infected people, the amount of people that could get infected is still like pretty much everyone. There is no type of herd immunity yet. And the number of infections grows approximately exponentially at this rate. So you can see that approximately what you're dealing with is this rate right here. And you can see both parameters are in this rate. So if you derive some number for this, let's say this, you derive from your data points that this must be 5. This is the rate at which the exponential curve grows. There are many settings of beta and d that make this number 5, right? In fact, there are infinitely many pairs that make this number be 5. So they say this is a classic example of underspecification, okay? There are many different predictors, each of which returns a good predictor on the data that you have. And you could split this into train and test. You could split these data points. You can say, I'll take 3 data points as a train and 1 as a test. And still, there would be many, many predictors that fit the data. Here you see 2 of them. So the blue and the red, they fit the data equally well right here. However, they have obviously very different trajectories. So they say this is an example of underspecification. And here already, like, I half agree. I mean, yes, if you do it like this, numerically, these look kind of similar, but it's like clearly one fits more than the other, right? So I'm not sure that is a good example for this underspecification, but you can give kind of the benefit here and say, okay, they want to give a simple model. So this is one of these models where it's underspecified. So it performs well on this data, but then if you look at this data, it performs drastically differently, right? That's the important part here, is drastically different. So if the real trajectory of the epidemic is something like this, then there is a predictor, namely d equal 28, that actually performs well, right? It's not that the training setup is different from the real world. It's that the variance of predictors is so large with respect to the data over here that there might be some that perform well, but the others perform pretty poorly. And they say this is not only the case for this initial fit, but if you do the same and you simply use a different initialization, so you simply use a different initialization for your parameters, namely you either use a gamma or a normal distribution, that will already turn out to give you very different results. So here, depends on where it was initialized, and different initialization distribution result in different distribution of predicted trajectories. So this is much more, I feel, an example of what they want to demonstrate. So here, depending on how you initialize the model, the resulting model that it tends to give you, right? They do many different runs right here, and you can clearly see that the blue curves that were initialized with a normal distribution are in general, kind of on average, significantly lower than the red curves, right? Same data, same procedure, same everything, but you get, in expectation, even different outcomes simply by how you initialize the parameters. I feel this is a very good example right here of what they want to say. Not so much the early training data, but you get the point that they say the underspecification leaves this variance, okay? Now, what would a good specification look like? So in this case, a good specification, would either be that you somehow have a theoretical reason for choosing one of these two initializers. This could one specification be that could solve the problem. Another one that is probably more practical one would simply be to incorporate data from over here, and thereby you know which model you should pick, which in an epidemic, it's not really, it's like, well, I can tell you how it turns out once I know how it turns out, right? Yeah, so, and that's a bit of a problem because it already shows you sometimes adding these more specifications or checking whether or not the model does what you want it to do in this specific axis that has a large variance is just not possible, like here. But the example is, it's the example. So the next thing they do is they analyze this in a theoretical model. So they have this theoretical model right here. This is kind of a two-layer neural network where the first layer is completely random, okay? This is random, this is not trained. What's trained is this thing right here. So it's sort of kind of a linear model. It's sort of a model of a neural network that people often use in theoretical analysis. You assume some kind of distribution on the data, and then you assume some kind of distribution on the weight matrix entries, and then all you do is you train the theta parameter right here, and you can make some theoretical statements about what happens with that model. So their goal here is to show that their goal is to show the following. So obviously, let's say we keep the same data, okay? We keep the same data distribution or the same data. We sample this W right here. Now, we can imagine W1, W2, W3. These are all different weight matrices, okay? So can we come up with a model that performs well on all the weight matrices that we would kind of throw at it, but that doesn't, but if we just plug in kind of different data, it stops performing well in one particular axis, right? So as long as we only look at the training distribution, we're fine, but then there is this one particular axis that the model just fails for some weight matrices, but not for others. Okay, so that's going to be the theoretical goal here, is to construct as closely as possible a model that conforms to the claims right here. So what they do is they make use of adversarial perturbations, where they say we construct a weight matrix. Where is it? We construct a weight matrix. Here, for any given weight matrix, a shift can be chosen such that it has a small norm, so that it's essentially the same data that goes into the model. 2, it leaves the risk of an independently sampled W mostly unchanged, which is exactly what we have specified, is that if I train the model and I simply evaluate it on my original data, then everything's fine, okay? But it drastically increases the risk of W0. So what it says is that if I have such a model like I have above, then I can construct a situation where I simply pick one weight matrix, say this one right here. I can derive a data set x0 or x, let's call that x3 for W3. I can derive a data set x3 such that all the other weight matrices will work just fine on that data set, right? They will work the same as my original data right here. Everything's fine. However, this particular one won't work on that data set, and that is going to result from an adversarial perturbation targeted at exactly that. So this thing here constructs a data set that is according to their own claims. Okay, so it's a cool thing to show that this is possible. If you have an over-specified model, you can generally construct a situation that exactly conforms to their claims. However, this is cool in theory, but I don't think they demonstrate this too much in the real examples right here. So, yeah, just maybe this was unclear. I'm not the best at explaining this type of stuff, but what you can imagine is that the weight matrices that you get out of your training procedure, they can be fairly different, right? Let's just call them vectors. So this is W1, this is W2, W3, W4, if your neural network just had two different weights. So the weight matrices can be drastically different, and the solutions to them can be drastically different, but I can construct kind of an adversarial data set that is, let's say, exactly into the, this is going to be very simplified, exactly into the, let's say, opposite direction of one particular weight matrix, so that it will work just fine with this weight matrix. It will work just fine with this, because you have kind of the projection onto them is well specified. But if I try to project it onto this one, maybe I should have drawn it exactly orthogonal, but you get what I mean. I can sort of target one of these models, and then by definition, that one particular model that is as good as all the other models on the regular data will fail for this particular data set, whereas all the other models will still work just fine. It's kind of a theoretical analysis by construction. Yeah, cool, but you know, if you make a claim and then you construct a situation that exactly conforms to your claims, then of course it's going to conform to your claims. Yeah, so this is more according to the real world. So this is a medical genomics example where you can see the training data. They have training data, they have evaluation data that comes from the same distribution, and then they have evaluation data that comes out of distribution. So this is more like a domain drift, domain shift example, okay? And our question is going to be, how do these things relate? So you can see that if you train on the training data and then you evaluate on the training data, you get, this is mean squared, normalized mean squared error, so lower is better. You get kind of a variance of models. So these are all the models that kind of come out of the training procedure. And the red dot is a specific heuristic that performs just a bit better. This is actually, so what it does is you have a bunch of data points, but the data points sort of form clusters. And what these methods do is they take one representative out of each cluster, like so, one representative, and then they train a model just on the representatives. And that's supposed to, just because these data points are all very correlated, if they're in the same cluster, that kind of gives a better performance. The red dot simply is a very special heuristic to choose that representative, whereas the blue dots here simply choose these representatives at random. So you can conceivably say that all these models, like the difference is simply how these representatives are selected. And you can see they all turn out fairly similar, with the red dot being just a little bit better. If you go to the test set on the same data, you can see the performance drops, but you know, still everything performs like pretty well. The range of performance here is fairly small. So all of these models, you would say they perform pretty okay-ish. But now you go to the let's say out of distribution data, and the range of performance is just very, very big. And the point here I think they're trying to make is that look at the best performing models right here. Look at them. They are on the level of the performance of your models in the test data set, in the in-distribution test data set. However, not all of them, right? So a good performing model would be in the models that you get, but you simply can't tell from just looking at the test data set. And that is according to their claim. And they have a further graphic right here where they show, look, it's not as easy as saying let's just take the best one here because that's going to be the best one here. So here a plot, they compare how well a model does and the eval set in distribution versus the eval set out of distribution. And you can see the correlation is, if it's there, it's fairly weak. So you would expect some line like this if that was just stretched out, right? If this thing was just stretched, you would expect like a line, but here there's just no way to tell for this particular data set. Okay, so that's an example of what they mean by under specification. However, I fail to see, I see that these low points right here are kind of on the level of the test distribution, but I am not I fail to see what the difference is to a classic data drift. Just because they are on the same level, right? I don't think it's that different. Like here, the mean performance simply drops and the variance between the models increases. And if I had a different eval set, the ordering would be different and it would look the same, but the ordering of models would be different and so on. What you'd have to do for me, I wonder, for example, is it the case in this step as well? So what here, if you did the same analysis, would it turn out that what performs well in the training data set also performs well in the test data set? Or is it also pretty random from the training data set to predict at least the order of test set performance? They never do anything like this. If this is substantially different here, then you can make an argument, well, this is a different thing than simply some sort of generalization. This is really kind of due to this under specification, because going from this data set to this data set, you sort of have a different spec. But to me, it seems that this is just kind of a domain drift problem. And if you look closely, actually the performance right here is lower than the best performance here, right? So that this technically does not fall under their definition if you go strictly. So I'm not really sure what to make of these sort of examples. I get what they're trying to say, but it seems to me that except for the theoretical thing where they construct the examples, it doesn't convince me that it's not just domain drift, okay? It's not just the same problem that other people have described. And secondly, it also doesn't convince me that adding the specification will solve the problem, because in the experiment so far, notice we have never seen a method from them to say, let's just fix the problem. Let's add the specification, and then we show that we can really keep this performance, right? The key thing is you want to keep this performance, but you want to bring this performance up, right? So far, we've had these kind of fundamental trade-offs, and these have often arisen in, let's say, explainability or fairness and so on, or actually domain adaptation. Is if you want to bring this down, a natural effect is going to be to bring this up. So, even if there are good models right here, it might be that in order to reach those models, you actually have to weaken the training procedure in order to consistently reach those models. That is not demonstrated in the paper that this is even possible. Okay, so they have a bunch of more case studies. For example, they have this kind of ImageNet-C example, where ImageNet-C kind of takes ImageNet and applies a bunch of random but, let's say, well-specified perturbations on it. And again, they show the same thing right here. They show that, look, all these models, they perform relatively equally on the just plain test set of ImageNet, but the span of these models, they are trained all the same, just the random seed is different, right? And they have a huge span of performance on these individual things. And what you'll notice also here or here is that it's not always the same model. So the model that is good at the pixelate thing will be not so good at the contrast thing, and so on. So the question is going to be, which the paper also doesn't solve, is going to be that, you know, these kind of stress tests, they are in very, very specific things like pixelate. I can think of a million perturbations to images that are kind of orthogonal to pixelate. It is going to be very impossible to specify all of them, right? To remove this underspecification. So the question is probably by adding the specification of pixelate, you simply worsen the problem for any of the other things that you have still not specified. Plus, you probably worsen a little bit your performance on the actual test set if you incorporate that into training. So the paper still hasn't shown that that is even possible. What is interesting is, here, they basically say you cannot predict the performance on one of these perturbations from the others. So they appear to be completely orthogonal. So it's not just enough to have a bunch of perturbations and then kind of be confident that the model is sort of robust to all the perturbations. I think the core message of the paper is that if you care about a specific axis, you have to go and check for that specific axis, right? Otherwise, you don't know what your model is doing. It could be doing something good, but it could be doing something bad if you don't specifically care about it. They do the same thing with kind of these skin lesions. So they have all kinds of demonstration here. In NLP, they do tests with BERT. And this is interesting because not only do they test different seeds for fine-tuning BERT, but they also test different seeds for pre-training. So in these language models, you have like a pre-training phase, and then you have a fine-tuning phase. And both of them have kind of random seeds. So they are going to show that even, let's say, the random seed of the pre-training will actually already play a big role in how these models perform in these stress tests. I find this to be pretty interesting. So they do this with respect to these gender data sets, which have been constructed to sort of assess fairness of these models. And so what you're going to have is data like the following. So you're going to have the sentence, let's say a doctor is walking. So it's always going to be like some sort of profession, okay, used in a sentence. And then what you do is you simply replace that entity with a man or a woman, right? You replace it twice. And you ask your model, you embed all of these sentences, and then you ask your model how similar are those sentences. I presume by simply taking the inner product of the embeddings, or you can actually train it. Okay, so they say part of glue, our ensemble of predictors achieve consistent accuracy measured in terms of correlation with human provided similarity scores ranging from this to that. Okay, so you have kind of a model that can predict similarity in text, just similarity. It knows nothing about gender, right? You simply train it on a data set to predict similarity in text. And then you ask it, so this sentence that I have here, this reference sentence, is it more similar to when I replace the entity with a woman, or is it more similar to when I replace the entity with a man? Okay, and what you look at is the difference between the two. So if this is a positive number, that means that the sentence is more similar to when you replace it with the word woman, and when you have a negative number, the same for man. And if the model is, let's say, insensitive to the gender dimension, then you expect a difference here of 0, at least in expectation, right? So A model that does not learn a gendered correlation for a given profession will have an expected similarity delta of 0. We are particularly interested in the extent to which the similarity delta for each profession correlates with the percentage of women actually employed in that profession, as measured by U.S. Bureau of Labor Statistics. Right. This is, in my opinion, this is already an improved assessment from what usually happens in these fairness literature things, where they just say, well, if it's anything but 50-50, we are angry, which I get it. If you some cases you need to build a model that is actually 50-50. But if you want to assess things like they assess here, like the question is, does the model spuriously pick up this thing? So if the model does something, like if the model is, let's say, perfect, and does only the task we need it to do, it will learn the association between a profession and a gender in the exact proportion that it kind of happens in the text, which I guess is proportional to the proportion at which it happens in the world. If, however, the model for some reason uses this thing as a feature more or less than it should, then we see a discrepancy. And why is that important? That it's important because if we then deploy this model, right, we simply take, so the model here is going to be, the axis here is going to be 0, and the model can perfectly solve the task by simply being here, right? It's actually best to be here, where this delta between the similarity and the profession percentage is 0. But the model can probably solve the task equally well by being here, or here, or here, or here, right? It can solve the task equally well. However, if we just happen to pick, at the end we pick one model. If we happen to pick this model right here, that model, just by more or less chance, has a much higher association with one gender to particular professions than the other. And depending on what we use the model for, like we seldomly use the model on the exact task and data that we trained it on, depending on what we use it for, this might cause some adverse effects. Okay, so I want to stress that this is not the same as your kind of classic fairness literature. This really considers all these models. They perform like equally well on the test set of that particular task. And since it's overspecified or underspecified, overparameterized, there are many, many ways to solve tasks. Some of these ways will include this feature. Some of these ways will include actually the opposite feature. And if we kind of pick one that's at the extreme, then the model is going to have that feature, and that might not be important for this task, but it might cause something bad for a task that we ultimately apply it on. So they do this similarity and they do pronoun resolution, and so they come up with different things. They say there is a large spread in correlation with BLS statistics. On the STS task, correlations range from 0.3 to 0.7. On the pronoun resolution task, the range is this. As a point of comparison, prior work on gender shortcut pronoun resolution found correlation ranging for that. Okay, so we are in the same ballpark as prior work. They say there is a weak relationship between test accuracy, performance, and gendered correlation. So there's a Spearman correlation coefficient of 0.08, which is a weak correlation, right? In fact, the confidence interval includes 0. Oh, that's for pronoun resolution. So for the similarity, it's 0.21, which is an okay correlation. The confidence interval just barely includes 0, so we're fairly sure. I'm not a statistician. Don't grill me about p-values. They say this indicates that learning accurate predictors does not require learning strong gendered correlations, which is a statement you can make, though I would say such a overparameterized, underspecified model will probably pick up this feature here fairly often, since the correlation is there, right? But they are right, it does not require strong correlations. Okay. And they say, third, the encoding of spurious correlation is sensitive to the random seed at pre-training and not just fine-tuning. So this is very interesting, especially in the pronoun resolution task. So the pronoun resolution task, don't want to go into it too much here, but so here you can see two different runs. So two different random seeds that result in two very different. So here is the similarity delta. This is this minus this we observed before, plotted against this percentage female by occupation for individual occupations. And you can see here, this predictor has a stronger correlation than this predictor right here. Now, I've thought about it. I'm still not sure which one is, let's call it the better one, because I'm not sure, like, because you can say the bottom predictor has less of a correlation with actual occupation. I think that makes it worse, right? But you might argue that a model just shouldn't depend or shouldn't care, but then the delta is not zero. Whereas this top predictor actually has the zero here at the point where it's 50-50. So I'm going to tacitly argue that the top predictor is the one you want, but I don't know. The important part, the paper doesn't make a strong opinionated claim about which one you want. The paper actually just says you should be aware that both predictors solve the task very well. However, they're drastically different in how they treat this feature. So here you can see there's not really a correlation between this score and the test set accuracy. You can't tell from the test set you can't tell from the test set how it's going to perform in this particular stress test. And this is very interesting. In the pronoun resolution task, they plot by different pre-training seeds, and you can see they clearly cluster, right? So even the pre-training seed has an influence later on this performance. I guess it's kind of logical, but it's still interesting to see that this clusters so well, while all these things solve the task the same. So that it basically means that you can't just take like a BERT checkpoint and then fine tune it with like an objective in there that you might already be worried about how the pre-training happened. I guess maybe you can fix it. I don't know. That's what they don't show. So they analyze it a bit more. They say they take 20 of those predictors here to better understand the differences between predictors in our example. We analyze the structure in how similarity scores produced by the predictors in our ensemble deviate from the ensemble mean. Here we find that the main axis of variation aligns at least at its extremes with differences in how predictors represent stereotypical associations between profession and gender. So these data sets, by the way, they are annotated. They are constructed such that the kind of stereotypes manifest or don't manifest, depending on how much your model has picked those up during training. Specifically, we perform principal component analysis over similarity score produced by 20 fine-tunings of a single BERT checkpoint, so 20 different models. We plot the first principal component, which contains 22% of the variation in score deviations against the female participation percentages in figure 9. Notably, examples in the region where the first principal component values are strongly negative include some of the strongest gender imbalances. So let's look at this graphic right here, because this is where I kind of sort of get skeptical. Okay, so let's understand these plots on the left right here. So what you have is the first principal component of this kind of this resulting similarity scores. So I'm going to guess each of these dots here is one of these models. So you can see, and I'm going to guess that each of these line is like one of these professions, okay? So for a given profession, like this here appears to be a profession where, let's say approximately, that has a 20% female occupation rate, and the spread here is going to be how the different models happen to manifest in the first principal component. So the first principal component, the axis of largest variation in the data set. So the first thing that is very notable here is that these models are spread out quite a bit, right? So they perform, like, sometimes it's very it's very negative, sometimes it's very positive for the same thing, right? This is what is strange, or this is a thing that this paper points out. All these models perform equally well on the test set of the task that they care about. However, so this here is when you put man as a subject. So up here, the 100, these occupations that are listed here would be something like, I don't know, mine worker, oil rig worker, or something like this. And on the bottom, you'd have kind of the more stereotypical female professions like nurse or something like this. So a couple of things to note here. So what they do is, the red dots here are theirs. So they say, we'll take the extremes, and the extremes are just whenever I think here is -1. So they take the extremes and they look at them here, and they kind of make a point of the first principal component in its extremes displays kind of the most anti-stereotypical examples, okay? So you have to see, here is, these dots are where the first principal component is loaded negatively by a lot. And the sentences, these are the red dot sentences, right? The red dots, those are those sentences. A receptionist is crawling is the sentence, and the plot is for man as a subject. So this is when you measure the similarity between a receptionist is crawling and a man is crawling, you ask how similar are those sentences compared to when I enter a woman is crawling. Sorry, compared to the similarity of a receptionist is crawling with a woman is crawling, right? So this is the data. This is fairly meta, right? So their claim is that this first principal component kind of incorporates this feature by a lot. And I think their point is kind of, see, even when we don't train this stuff, there are models that that very much rely on kind of these, or that very much over rely on these kind of stereotypes. However, this is very, I feel it's a bit shady, because I mean, look at this data, right? You can't just pick these outliers. Like here, these are outliers too, and even if you look here, like they conveniently pick. So I guess they conveniently pick such that these things here are left out. You can see here it's woman as a subject. So what you'd expect here, if this is really the models pick up a lot of these kind of spurious correlation, what you'd expect is a line like this, right? You have like shift here and then up here, because 100% women, like the first component will load a lot. You don't see that at all, right? And here you see a little bit a slope like this, but I don't think that and especially if you look at the noise between the things, like this is here and then this is over here, right? So like the in-between noise is way bigger. To go and claim, the first principal components contain something like this, and then we don't look at these outliers up here, I don't know. So this doesn't seem to me like, I see what they're trying to say, and what is concerning is that there is such a big spread among the models, right? Within these professions, there is a giant spread. These are the same performing models. So I see what they're trying to say, but I don't think the point they're making here, I don't know if this is politics or something that they have to kind of bring in these types of topics, but they also look at with respect to others, and they show, these models perform differently with respect to different stress test dimensions, and notably the ordering isn't the same. But again, I feel that this is simply, this might be just a problem of domain shift rather than what they're claiming. And lastly, they have kind of a test on these other stress tests that are also NLP stress tests. And you can see that the models perform quite differently. So there's a spread right here. Within each of these, the red bar is the spread on the actual test set, as I understand it. And then these are the different pre-training seeds. And you can, again, see that even the pre-training seed will have a big effect right here. So, yeah, again, what I would like to see is kind of how, does even the training performance predict the test performance on the same distribution? That would already be quite informative. As you can see right here, you can't really predict one of these stress tests from the other. The question is just, can you even do this for the training to the test set? Because that would inform you whether or not this is a property of this stress test being in a different direction, one direction that you didn't capture. If these stress tests are really meant to show that, look, you can't really tell this axis that you didn't specify. This is really because of underspecification. You would expect that from the training performance, you could at least predict the test performance somewhat. Or from the test performance, you could predict on an IID test set. I'm going to assume that it is somewhat like this, but I'm also not sure that that this is anything to rely on. And the last thing they do is kind of a lab study where they have kind of vital signals and they predict whether or not there is a medical problem. And again, you can see here they even test different architectures and so on. And what they're basically the point is the same, but it's just shown in a different data. It's pretty cool that they have lots of different examples right here, but I don't want to go into the lab thing. So their discussion at the end, I think, is kind of weak, because I mean what they say is our findings underscore the need to thoroughly test models on application-specific tasks, and in particular to check that the performance on these tasks is stable. I mean, I fully agree with that, right? If you deploy your model into some sort of real-world application, please test whether it actually works in that real-world application. But it seems to me that it's not a solution fully to the problem, because as we saw in the epidemiology paper, that sometimes just isn't possible. And also, it is the case that not everyone can train a language model, so we kind of need pre-trained checkpoints. Maybe the goal is that we provide, like maybe Google, if they provide one BERT checkpoint, let's say they provide 50, right? And then people can go ahead and check which one actually is good or bad on their particular dimension that they care about, that maybe the pre-training didn't care about. I think that would be a practical solution to the problem if you can't specify it. And what I would say also is that it's not clear to me that it is always possible, even in theory maybe, but it is not clear to me that it is always possible to add the specification that you want and keep the same performance. I see that there are predictors in the set that they consider that have that, but that doesn't mean that once you add the constraint, the training procedure reaches that same performance and specifically keeps the performance on the test set. So that's kind of a number of criticisms on this paper. All in all, I mean, it's a paper that you generally can agree with, right? Can agree with the sentiment and also the analysis. The examples are, of course, real, and the problem is real. And especially for a company like Google, this is fairly important because they build big models and deploy big models. All right, let me know what you think about this. I'll see you next time. Bye-bye.